Okay, so linear approximations, it says there are times when we're interested in finding just a small, the effect of a small change. For example, how is the revenue at your local theater affected by a small change in the ticket price for a movie? We can explore an application of the tangent line to a function called the linear approximation. And it says we've already seen that a curve lies very close to its tangent line near the point of tangency. So we know that that's super close right there. In the function at the left, we're interested in the change where delta x is small. By definition, the derivative is the limit. So you can read this, but really the most formal definition and the easiest one to understand is on the next page. Okay, up at the top, linear approximation of delta f. So if f is differentiable at x equals a, meaning we can take the derivative of it, and delta x is small, then delta f is approximately f prime of a delta x, where delta f equals f of a plus delta x minus f of a. So I know that is crazy. You guys are probably dying right now just listening to me say that. I know what you would be doing in class. All right. So it says, this is sometimes referred to as the tangent line approximation. In other words, we use the tangent line at the point of tangency as an approximation to the curve where x is very, very near to a. So we're just seeing that small change. And it says, remember that the point slope equation of the tangent line is y equals f of a plus f prime of a times x minus a. So in the last examples, they had f of a on the right-hand side, like adding it at the end. It does not matter. You can do it either way. Okay. And then L of x, you might hear Campbell in the background, or her movie, sorry. So L of x is just the linear approximation. And so this says the exact same thing that we just talked about. That's our equation right there. So for example 7, it says to find the approximate value of the square root of 26 without using a calculator. So this, I know you guys are probably thinking this is stupid, but this is just an exercise to get you familiar with how to use this approximation. So our parent function, if we were to look at the square root of 26, we need a function to go with it. So we'll say that is y equals the square root of x. That's our parent function. Step 1, we're going to rewrite the square root of x as x to the 1/2 to find the derivative using the power rule. So when you do that, if you have x to the 1/2 and we bring that 1/2 down in front, you'll have 1/2 x raised to the negative 1/2. And we know we've done that enough to know that it's 1 over 2 square root of x. Okay, step 2, we're going to plug in 25. Because now I made a little note over here, we're going to use 25 as the x value because we know it's a perfect square that's close to 26. Since we're working with square roots, we want to have something concrete that we know. So we'll plug in 25. And when we do that, we get 1 over 10. Okay, since that's f prime, that's our slope. 1 over 10 is our slope. Okay, so that goes here. We know our x value is 25. So that would go there. And to find that y value, we're plugging in 25 to the original equation, so the parent function. So the square root of 25 is 5. So here's our tangent line. And we want to use that tangent line to approximate the value when x is 26. So if we did that, we'd plug in 26 for x. And we'd get 1/10 or 0.1. Times 26 minus 25 plus 5. 26 minus 25 is 1. That gives us 0.1 plus 5, which is 5.1. So that is the approximation. And if we look at the actual value of the square root of 26, if you put it in your calculator, it's really close to that. It's 5.099. And so I want to go ahead and show you this before we move on, because I think it's in the next example. It is. Where you're going to need to know how to judge the approximation. So if we look at the graphical representation, here's x is 25. We're just pretending this is the exact value right here. Here's x is 25. Our tangent line would be right here. And so that tangent line lies above the function. So the function square root of x is this, that black line. Our tangent line is above it. So that means our approximation is going to be above the actual value. So like this, 5.1 is a little bit above 5.099, but it's a very good approximation. It's pretty close. All right, so if it was below, it would be an underestimate, which is important in this example. So example 8 says to find the tangent line approximation for the function f of x equals 2x cubed minus 3x at a equals 1, or x equals 1, whatever you want. So we're going to use the result to approximate the value of f of 1.1. And we want to know if that approximation overestimates or underestimates the actual value of 1.1. And how do we know? So step 1, we always want to find the derivative. So if we find the derivative of 2x cubed minus 3x, we're going to get 6x squared minus 3. All right, so step 2, we're going to plug in our x value, which is 1 right now. So we'll plug in 1, and that's going to give us 3, and so that's our slope. Okay, so we have our x value at 1, our slope is 3, and step 3, we're going to find our y value. So we're plugging in 1 to our original equation. Okay, so when we do f of 1, we get the y value as negative 1. So we can use these three things, the slope, the y value, and our x value at 1, to write the tangent line. So slope is 3, and then we have x minus 1. Then this time it's minus 1, because that's our y value. Alright, so we want to use that tangent line to approximate the value of 1.1, just like we did in the last example. So we plug it in, and then that is going to give us negative 0.7. So our estimate is negative 0.7, and we want to know if this is an overestimate or underestimate, and we want to see how we know. So if you were to look at the graph, either on a calculator and sketch it or whatever, it would look like this. This is our graph right here, this squiggly line. So if we had a tangent line at the value where x is 1, here's x is 1, it would go right here at 1, negative 1. We know that's our point. Okay, so when we look at that, that line is under the actual function. So the tangent line is below the function, which is going to make negative 0.7 an underestimate. Okay, if it's over the function, like if it was over here, at whatever x value that would be an overestimate. But this one is an underestimate because it's below the actual function. Example 9, by approximately how much does the area of a circle change when the radius increases from 4 inches to 4.01 inches? So first of all, we need to know the area of a circle is pi r squared. Okay, so then we're going to take that and we're going to find the derivative first. So that's 2 pi r. Step 2, we want to find that y value. So to find the y value, we plug in 4 to our original. So that's this one up here. So it'd be pi times 4 squared, which is 16 pi. To get our slope, we want to plug in 4 to our derivative. So that gives us 8 pi. And then step 4 over here, we want to write the tangent line. So it's y equals 8 pi. And then x, or this time it's r because it's radius, r minus 4, because that's our x value right there, or radius. And then we have plus 16 pi. Now we're going to use this to approximate when the radius is 4.01. So we just plug that in. And we get 8 pi times 0.01 plus 16. And if we type all of that in our calculator, the pi included, use your pi key, you're going to get 50.5168. So here's when it's 4.01. And then when it's 4, remember it was 16 pi. So you're going to want to do 50.5168 minus 16 pi in your calculator, and you will get 0.2513. And this is our final answer. That is how much it increases as the radius increases. So the area increases by that much. Okay, last one. The equation 10x minus 0.5 equals negative 2 times y plus 4. That represents the equation of the tangent line to the graph of g of x when x is negative 1. And it wants to know what is g prime of negative 1. So remember, when we do the derivative g prime of a number, that's going to give us the slope. So we have our x value as negative 1, and our slope is what we want to know. So, oops, those are the answers. It's not what I want to cover. So all we have to do is we take this equation that I highlighted in blue, and it says to use that equation, I didn't mean that, to solve for y. And then you'll be able to see the slope. So remember, the slope is the coefficient in front of the x value. So if we do that, we set this equal to each other and get everything to one side. We get y equals something. We're going to divide everything by negative 2. And that's going to give us negative 5x minus 0.25 equals y plus 4. Even if we subtracted 4 from here on both sides, our negative 5x is going to stay unchanged. Okay, so we know that our slope here, which is g prime of negative 1, is negative 5, which is answer A. Okay, so remember, if you have questions, message me. Hopefully we'll have another Zoom chat if we need to. That's going to be our discussion this week. So get started on these, and I'll talk to you soon.